One of the biggest advantages to understanding equilibrium is once we get a little bit of a feel for it, we can look at ways that we can manipulate it. We can make things do what we want to do based on their equilibrium behavior. So let's take a look at a problem. You're studying the reaction A goes to 3B. I simplified that problem down so we've got fewer things to talk about. When the reaction reaches equilibrium, you find that the concentration of A is 0.167 molar, the concentration of B is 0.979 molar. At this point, you reach in and remove 0.684 molar of B from the reaction. Is the reaction still at equilibrium? Now, before we even look at any mathematical details here, it better not be at equilibrium, right? I've just reached in and removed a bunch of product, a bunch of B from the reaction, so it can't be at equilibrium anymore. So simple answer is no, it's not still at equilibrium, but let's explore that a little bit more. We've got numbers, so let's go ahead and calculate the equilibrium constant. KEQ is B raised to the third power, because of this 3, divided by A raised to the first power, because that implied 1. Plugging in our values, I get KEQ of 5.62. Well, now, if I remove that handful of B, I can calculate a value of Q. So plug into the same mathematical form. Now I've got 0.979 minus 0.684 cubed divided by 0.167. So this subtraction is 0.295. Cube that, and I find the value of Q is 0.154, which is less than 5.62, which means, number one, it's not at equilibrium. Number two, this reaction has to shift towards products to get back to equilibrium. And that makes sense, right? I've removed some product, so to get back to the balance, it's going to have to shift towards products. It's going to have to react more to get back to equilibrium. And this is a really convenient way, practically speaking. When people are doing chemical reactions, one of the ways to get the reaction to happen more is to just look at ways to remove B. And when we remove B, we get more of A to react. So that's one of the important ways we can manipulate equilibrium. This type of manipulating equilibrium is encapsulated, is described by Le Chatelier's principle. So when a system is at equilibrium and it experiences a stress, the reaction will shift to relieve the stress, if possible, that it just experienced. So what do we mean when we say stress? In a Le Chatelier's principle sense, when we say stress, we can impose a stress on a system by adding or removing a reactant or product. We can change temperature, and we can change pressure. So we'll take a look at a couple quick examples, but really, if we think about Le Chatelier's principle, this is a chemical principle, but we can use this same type of description to describe a lot of other systems, whether we're talking about, if we're talking about like an ecology type of application. Le Chatelier's principle is essentially carrying capacity of wildlife. If you have too many deer, that's a stress. Some of them are going to die to relieve that stress. You can also use it in finance and economics. If a system at equilibrium experiences a stress, it'll shift to relieve that stress. If your budget is balanced and all of a sudden you have an unexpected large expense, well, you might have to pick up a couple extra hours at work to relieve the stress of that extra added expense. So we can use the idea of Le Chatelier's principle in a lot of different areas. We're specifically looking at it in chemistry. So let's go back to the problem we just looked at, right? We have a system at equilibrium. So a system at equilibrium, it's going to experience a stress. We've removed some B, and it will shift to relieve that stress. So it'll react more to get there. So there is adding or removing a reactant or product. What about changing temperature? Now, changing temperature, we can think of this as a whole different process, or we can try to think about it the same way. So when we're changing temperature, we can think of heat as being either a reactant in an endothermic process or a product in an exothermic process. So if I've got sodium +1 ions and acetate ions in solution, they can combine to form sodium acetate, and it looks like I forgot to do subscripts, solid. So they can precipitate to form a solid, and that liberates heat. Well, in this case, heat is a product of this reaction. So what happens if I increase the temperature? If I increase the temperature, I'm adding heat. Heat is a product. If I add something to the product side of the reaction, it's going to shift to the left to relieve that stress. So changing temperature is really just using heat as a reactant or product, and it works the same way as any other reactant or product. The one that is a little bit different is pressure. So changing pressure will only affect a reaction if the reaction has gas particles in it. So when we've got a reaction with gas particles, so 2 NO2 gas can combine to form an N2O4 gas. If we increase the pressure on the system at equilibrium, the reaction will shift toward the side with fewer gas particles because it's trying to relieve that pressure. It's trying to relieve that stress of more pressure. How does it do that? By decreasing the number of gas particles. So in this particular reaction, there are 2 gas particles on the left. There's 1 gas particle on the right. If I increase the pressure, this reaction will shift towards the side with fewer gas particles, towards the products in this case. So this is another way for us to push a reaction towards completion. So changing pressure only affects things with gas particles, and probably more importantly, only affects things with different numbers of gas particles on the 2 sides of the arrow. Because if there's the same number of gas particles on both sides, changing pressure isn't really going to do much. So that is just a little bit on Le Chatelier's principle, and how either adding or subtracting a reactant or product, changing temperature or changing pressure can influence a system at equilibrium. Again, we're not going to spend a ton of time digging into deep details of equilibrium and manipulating equilibrium, but it will come up in a number of the other topics that we're going to address in the course. So see you next time.